Hello everyone, my name is Artem Chirkov, and I'm here to present a joint work with Gregory Rosenblatt, Matthew Might, and Lisa Zhang. The work is called A Relational Interpreter for Synthesizing JavaScript. First of all, a quick summary. In our study, we introduce a miniKanren relational interpreter for a subset of JavaScript that is capable of synthesizing imperative S-expression JavaScript code. We then explore its ability to solve small problems. Going into this project, we wanted to try our hand at making a relational interpreter for a full-scale imperative language. Additionally, JavaScript is interesting to us because it has a set of quirks that might pose a challenge for inexperienced programmers, and we wanted to build an interpreter with these quirks in mind. Today we will focus on the specifics of interpreting imperative languages and on the lessons we learned in the process. Hopefully, you too will learn something useful for your next interpreter project. Without further ado, let's jump into a quick demo. Okay, first of all, I want to show you a quick example of running JavaScript forward before we get into the real meat of running it backwards and code synthesis. There is one unusual thing about our interpreter. It accepts S-expression JavaScript instead of normal JavaScript as input. So what is S-expression JavaScript? S-expression JavaScript is just our own notation for writing JavaScript code. It closely adheres to normal JavaScript syntax and semantics, and just saves us the trouble of lexing and parsing imperative code. I can demonstrate on an example. Consider this normal JavaScript code. It is a function. It accepts a single parameter x, returns 2 plus x, and we call that function with the number 42. How do you go about writing something like that in S-expression form? So we start by writing the most top-level expression, which is the function call. We call some function with the number 42. Makes sense so far. How do we define the function itself? Actually, almost the same way as in normal JavaScript. We type in function x, and then we have the body of the function. What do we have in the body? We have a return statement, right? Return. And I want to write 2 plus x here, but unfortunately, if I want to use a primitive operation, I have to declare that explicitly by typing in OP for operation, and then specifying the operation itself, plus. And then go the arguments, 2 and x. This is in sort of a prefix notation. Okay, looks good. Let's try running it. We should get 44 back. Let's see what we actually do get back. Okay, we get back something a little bit weird. This is a binary number in Little Indian notation. It is an internal representation of a number, and to convert it to a human readable form, we have a helper that we can map over the output. We call that helper humanize. Alright, let's see what we get. We get a number 44, just as we expected. Looking good so far. Let's jump back into the slides. As it turns out, our interpreter is actually a combined relation. It joins together two relations, parser readable and eval. Parser readable is a relational parser, also called disjoint, which links S-expression JavaScript code to its LambdaJS code representation. And eval is a relational interpreter which runs LambdaJS code. The question on everybody's mind right now is probably, what the heck is LambdaJS? LambdaJS is a minimal language introduced in the paper The Essence of JavaScript by Guha et al., through which any JavaScript code can be expressed. Using it as an intermediate helps us reason about the execution better, because it has much more straightforward semantics. Writing both of these as relations enables code synthesis. We can run eval backwards to synthesize code that evaluates to a certain result, and we can use the relational disjoint as a sugar which turns LambdaJS back into S-expression JavaScript or fills in the gaps. Your second question is probably, why the heck do we even bother with S-expression JavaScript when we are already using LambdaJS? The answer is on the next slide. We don't start off with LambdaJS because it is very minimal and looks more like functional assembly than JavaScript. On the left you can see the program from the demo, and on the right is the very same program expressed through LambdaJS. Hope you're glad we're not starting off with this mess. Well, now that we have an idea about how the interpreter works, why not try running it backwards? And to spice it up, let's make it a challenge. Here's my challenge to you, dear human listeners. Can you make this JavaScript code return undefined? If you're unfamiliar with JavaScript, let me do a quick rundown. First of all, we have a function definition and the function call. The function is called with the number 42. The function accepts a single parameter, x, and returns the result of executing the inner function. The inner function accepts no parameters and has two statements on the inside. An if statement, which has an always false condition and the blank space in the body, and a return x. So the question is, can you put a single statement in the blank to make it return undefined? In most programming languages, this would not be possible, but for better or for worse, that's not the case for JavaScript. I'll give you some time to think while the interpreter is synthesizing a solution. We'll actually synthesize 5, but there are many more than that. Okay, 3, 2, 1. Come on, please. Okay, we get back our results. The one I want to focus on is the simplest one, var x for now. Okay, var x. In normal JavaScript, this is equivalent to var x semicolon. Why does this work? Var x is just a way of declaring a variable in JavaScript. It's a bit of a node syntax, and it uses a special feature called hoisting. Essentially, before the function is ran, the interpreter scans the function body and finds all the variables declared with a var and allocates them. So it scans through our function, finds var x, and says, okay, before the body is executed, allocate x, and initialize to undefined. And since the x that is returned is now the function-wide new declared x, we get back undefined. Hope that made some sense. But what about the other solutions? As you can see, they are all using the same var hoisting trick, but they put something else on the right side. This one is trying to put some kind of symbol on the right side, which is probably a variable. This one is trying to put a true, this one is trying to put a false, and this one is trying to put a primitive operation on the right-hand side. Why do they work? So the thing is, with hoisting, only the allocation itself is pulled up. The initialization on the right-hand side is not pulled up with the allocation. So since this will not run, will not get executed because the condition is always false, we will still get back undefined. Okay, I hope that was fun. Let's get back to the slides. One big way in which functional and imperative languages differ is in how they handle their memory, and LambdaJS is no exception. Memory effects are threaded through execution, and any memory operation can affect any subsequent memory operation. If you look at the diagram once again, you will notice that eval exposes a parameter called store, right here, which is responsible for keeping the state of memory after execution of the program. Why do we need the store, and how do we use it? Please look at the next slide. Consider this simple program. It features multiple memory operations, some of which are not explicitly spelled out, as we are about to see. As a result of execution, you probably expect to get back an object where the string foo is mapped to the string bar. But actually, if we execute it, we get back a memory reference instead. To get the actual value, we need to peek into the store and find the corresponding value. This reference represents a memory address 2 as a piano numeral 0, 1, 2. And to get the actual value, we need to index into the store at the position 2. As you can see, there are other things in the memory which we did not put there explicitly, but that are still there. As you can see, there is an object, but it looks a bit different from what we expect. That is because it is a dual LambdaJS object, and they have two fields: private, which keeps the data relevant for the interpreter. For example, it can store a call field, which keeps the function called when the object is called. Yes, in JavaScript, all functions are actually objects with a special hidden field. Also, there is a public field, which stores the actual thing we want, our object containing foo mapped to bar. So, what did we learn in the end? Here is lesson 1. The parser almost entirely constrains the program structure. At some point in development, we were concerned with performance. As you can see, some problems took up to 5 minutes to synthesize, and some of them never finished synthesizing at all. So we thought, maybe some interaction between the two relations is slowing down the process. And we ran the benchmark on synthesizing LambdaJS directly. Can you guess the benchmark results? Well, your guess is about as good as mine actually, because most of them never came back at all. And the ones that did actually were slower than the original ones. Why did it happen? Since most of the constraints are set by the parser, the search space for a LambdaJS interpreter is too large. The verbosity of LambdaJS is actually making it harder to synthesize LambdaJS programs. With every level of nested code, the search space grows, and since actual JavaScript relies much less on nesting, it is actually easier to synthesize JavaScript programs. Lesson 2. The ordering of condy branches in the LambdaJS interpreter does not affect JavaScript synthesis performance. This one is pretty straightforward, leading from the previous one. Usually the way you optimize relational code is by arranging condy branches. However, since the LambdaJS code itself is generated by the parser, the only thing left for the interpreter is to execute it. In fact, very few decisions are made by the interpreter, and therefore the order of condy branches in the interpreter does not matter. Conversely, the order of branches in the parser matters a lot. For the third, final lesson, let's jump back into Emacs for a sec. Lesson 3. The parser-interpreter combination is not refutationally complete. What that means is that if a program does not have a synthesizable solution, that the search will never terminate. Consider this function. It's a function that has two statements in its body. The first one is return false, and the second one is a blank, which we are trying to synthesize. If we ask it to return true, it will never finish searching for a result, because there is nothing you can put in the blank that will make it return true. However, since the parser does not know that it is in a dead end, it will try nonetheless. But it will never find anything. You can actually try. As you can see, nothing is happening. Nothing is popping up for this fairly simple program. And we as humans know that there is, in fact, no solution to this. So let's kill it before it's too late, before it eats all of my memory. On that said note, thank you for listening. If you want to get in touch, feel free to use any of the contacts on the screen. Once again, thank you.